Hello, good evening. Can you hear me? Okay, good. So let me first of all share my screen with you. And today we are going to have a lecture, therefore there will be a presentation. So and I need to switch on this presentation, which we discussed last time. So I guess this is going to be this one. Okay, this one. Okay, I hope you got the file which I sent to you today, and that file, Excel file, it contains your grades for home assignments. So as you know, as I have already said, I decided to be a little bit more loyal than I usual, and I decided to normalize grades. So right now the highest grade is 10, and then that's actually increased your grades a little bit. So generally, my general comments is that your major drawbacks, and you all made the same mistake. The common mistake was that not all, but the majority of students made the same mistake. In the first question, we discussed this already. In the first question, you somehow ignored my comments about yearly yearly periods instead of half-yearly periods. There was a yearly period, and then you also somehow in the second question you missed this very important observation that the second coupon bond has maturity 8 years, and you all decided that it will mature 5 years from now, and then at the 5 years you'll get face value. So that's were common mistakes. However, I still I have still half accounted for these points, for the last 2 points, because well, something was right. I mean, the first coupon bonds was calculated, everything about first coupon bonds was calculated correctly, so I decided to give you half points for these points as well. But overall, these 2 mistakes were very common. However, some students managed to be mistaken in the easiest questions, like question 1.c about coupon term structure and the comparison of the British and the Russian markets. That's really, I think, most disappointing, because these questions were purely observations and analysis, nothing else, no calculations. So that's probably very disappointing when you made a mistake in these points. But overall, I believe that the overall grades, the average grade is okay. No, yeah, there will be no second home assignments, because the only home assignments will give you the grades with the weights of 40%, and then at the end of June, I think the 25th of June, on that date you will have final test. And the grades will be 60%. That's it. No other room for any other grades except for participation. So if you participate and we still have some tutorials, so you still have a chance to participate in tutorials with home assignments, and if you show a correct solution for one of the next home assignments, well, then I will a little bit increase your grades, but probably I will not give you 1 point, because for 1 point you should have been active throughout the course, but still, so just bear this in mind. I think we have already started this lecture. So this is we have 2 more topics overall to the end of the course. And the first topic is portfolio theory. So this is the first topic, portfolio theory. And then also we will talk about CAPM. I think some of you know something about CPM, so we will. I think this should not be difficult for you. Though I'm going to present it at a master's level, so not real easy. But anyway, the last but one, the last but one topic is portfolio theory, and since the majority of students don't know the portfolio theory, I first narrated at a bachelor level as if you have never heard about the portfolio theory, and then I will switch to the master's level narration at an increased level of difficulty. However, first we will discuss the portfolio theory at the bachelor level, but I remember that we have already covered a couple of slides last time. So these slides, well, this is just, this slide is about how popular the portfolio theory is. I have already made a statement that do not be confused that some, well, some students, probably some even those who already work in companies or with companies, they think that the portfolio theory is outdated, but actually recent research, well, it's not a research paper, recent questionnaires revealed the results that at least in Europe, the portfolio theory is widely used, has been widely used, and there is no trend to switch to some other to massively switch to some other asset management tool. And also in America, I think this is also the case, at least if you check for the Yale University. You probably know that you have probably heard about something which is called endowments. In Russian, we say целевой капитал. So endowments is kind of funds which is owned by non-profit making organizations like universities, for example, and the HSC also has its own endowments funds. So the endowment funds are usually accumulated with donations, and the largest donator for the HSC is the obviously the VTB bank. And then when such an amount of money is accumulated, the funds is transferred under management by some asset management company. And in our case, the VTB bank is the major donator, and also the VTB asset management company is the company which manages the HSC endowments. So what I wanted to say is that the Yale University endowment is one of the largest in the world, and actually, I think it's well, actually, if we take the 5 biggest universities in the UK, not in the UK, in the USA, and just sum up 5 or probably three universities: Yale, Harvard, yeah, it's Ivy League. So it's Yale, Harvard, and one more. Well, what's the third very famous university in the USA? Just it dropped out of my mind. Stanford, right? Stanford. So if we sum up their endowments, then in total they will be equal to the. I mean, their size will be equal to our national wealth funds. Российский фонд национального благосостояния. So just for you, I hope you're impressed. And anyway, so if you search for if you browse through the reports which are issued by Yale, they are supposed to issue yearly reports about where they describe how they manage their endowments funds. They always say that they employ the Markowitz, the portfolio theory model. Yes, exactly, as much as the Russian sovereign funds. Yeah, okay, like that. By the way, I think you have your national funds, Zhao, is called the Chinese investment company, something like that, if I'm not mistaken. Okay, and I know that it's bigger than the Russian National Wealth Funds, and I know that it's not based on oil revenue. Well, our fund is based on oil revenue, but your fund is not. And by the way, Zhao, I have checked your your email which you sent to me today, and you are right in your calculations. So good job, and your conclusions are also correct. So anyway, so if you just don't believe me, if I do not sound very convincing, just take some reports from the Yale University. And by the way, the Yale University endowment management is considered to be one of the most successful asset management process. So you just can believe them if you don't believe me, but you can browse through their reports and see that they always say that they employ the portfolio theory. So this is just for you to understand that it's really important to study it. And we started the narration at a bachelor level. So recall that these are our, well, I know that we have already passed these two slides, so I will be very quick. So we have these three types of utility functions, but we are interested only in this type because this type of the utility function represents a risk-averse investor, and we know that most people are risk-averse. So they actually govern the demands and supply. Well, they actually govern the demands for assets. So and therefore they govern the pricing process. Or mispricing process is if they are not quite adequate. But still, anyway, we're supposed to work with this curve. And if we want to translate this curve to another plane, to this plane, then and this plane is measured with a different unit of measurement. So here we have expected return and risk. So risk can be measured. Risk is uncertainty. The source of risk is uncertainty, and uncertainty is just because we don't know what's payoff will be in the future, because we're talking about risky assets. We are not certain about payoff. We might have high payoff, low payoff. So uncertainty can be the degree of uncertainty can be characterized by this variability of payoffs, the dispersion of payoffs. So, and you know, the dispersion is measured by variance or standard deviation. So in this case, it's standard deviation. If it were like that, so squared, then it would be a variance. But and we can actually work with a variance as well, but usually we work with a standard deviation. And therefore, let me remove this. So if we want to translate this graph to the right plane, from the left hand plane to the right hand plane, then we will get something which is called indifference curves. And to these two indifference curves corresponds to the to this utility curve, which describes some a risk-averse investor. So this two indifference curves also describe a risk-averse investor. So which is quite logical. The larger the risk, the more return an investor requires in order to be satisfied at the same level. So the indifference curves mean that you are always at the same level of satisfaction or satiation, and therefore more risk, more return, which is quite obvious. So just remember these two curves, because I'm going to employ them a little bit later, but now just remember that these indifference curves for a risk-averse investor looks like that. Okay, so now let's move further, and here we have a simple case when we have just only two risky assets, and that's it, no other assets, and therefore we need to assign weights to assets 1 and asset 2, so just the amounts of money relative to the total amounts of money. So it's a proportion. MI and MJ are just proportions, and we need to assign proportions to two risky assets. But we know that if there are only two weights, then the second weights can be represented in terms of the first weights, which is very convenient. And then we can calculate the expected return on our portfolio, which consists of two assets, and dispersion or variance of returns of our portfolio, which consists of two assets. And these are just pure econometrics. You know that the expectation of the sum is equal to the sum of expectations. And as for the variance, it's also a bit more complicated to decompose a variance of the sum. So the variance of the sum is equal to the sum of variances. So the sum of variances, and also we need to add two covariance terms. And also if we want to, and the weights are constants, so if we want to remove it, to put it in front of the variance, again, recall from econometrics, then in this case we need to square these constants, so that's what we will get. And then just I write the same formula using this standard notation sigma. So sigma means variance. So when we have this 2i, it's just like, you know, this is a variance, because we can actually write it like that. Si multiplied by si. So that will be si squared, so that will be variance. So this is just annotation for variance. Sometimes I can just write like that. This is also will be an annotation for variance, but this is also a possible notation for variance, and that's how I write it. So if you have question at this point, just you can ask, and if you don't, then we'll just go further. So do you have any questions? Okay, looks like not. Okay, so we can express expectation of the portfolio, expected return of the portfolio, and variance of the portfolio. But now, so we have two equations. But ideally, we would like to have one equation, because we want to draw a graph. So, and we are going to have this plane. So this plane, where here we have expected return, and here we have either variance or standard deviation. But again, let's have standard deviation, because that's how it's commonly done. So we have standard deviation here. So these two equations should be could be so either we can use a system of parametric equations, which is quite possible, or we can just try to combine these two equations together. And what we can actually do, you can try it at home, but this is just not necessarily for this course. You can just see that, for example, from this from the first equation, we can actually express weights. So we can so for example, we can express weights. You know that here we can just write 1 minus mi here instead of this weight. And then we can actually express weights in terms of this, and this. And then we can substitute weights here into this formula. And then we will get a very complicated, well, not very, just kind of complicated, long and clumsy formula. But this long and clumsy formula will be just the only one. So variance will be expressed in terms of weights and expected return as well. So, and if you just try to do it at home, you will see that you will come to a quadratic equation. So a quadratic equation has the form like that. So quadratic terms in x, quadratic terms in y, plus obviously xy, plus so in addition to quadratic terms, we also have linear terms. So a, b, c, d, so it's d, dx plus ey plus finally constants, or the intercept coefficients, which should be f, and all this is equal to 0. So this is a typical quadratic equation. And we have three types of quadratic equations. I mean, we have three types of graphs and three types of quadratic equations. ellipse, parabola, and hyperbola. Which form we will get depends on the sign of these coefficients. And in our case, the coefficients will be presented in this particular case, in this one. The coefficients will be presented in such a way that we will get strictly hyperbola, not ellipse, not parabola, but hyperbola. And therefore, let's move here. So this is our hyperbola. It will look like that. We actually have two. This is one half of hyperbola. That will be another half of the hyperbola, but it defines on negative standard deviation. So this area is negative. So it just has it has no economic meaning, and we will not work with this part. So we will only work with with this right hand parts of the hyperbola, right hand sides of the hyperbola. So this is so this hyperbola, what does it represent? So once again, this hyperbola represents a linear dependency of expected return upon standard deviation. So essentially, this hyperbola represents all possible combinations of two assets. So we have assets I, we have asset J. So it will essentially represents all possible. So each point will correspond to one portfolio. And this portfolio can be described in terms, for example, this portfolio, it will be described in terms of expected return and its risk. So risk measured by standard deviation. So just once again, I would like you to understand that all these points are just kinds of portfolios which we try to describe in this plane using these two parameters, expected return and standard deviation. And once again, these points are just like all these points. So why we get the hyperbola? Because of this transformation. So if we want to get something like that, so expected return as a function of standard deviation. Actually, this is expected return as a function of standard deviation, and then we get this hyperbola. And well, the thing is that or actually it will be just the other way around, because let's remove it, because we actually make a substitution into variance, not into expected return, but into variance. So in this case, variance will be our dependent variable, and then it will be a function of expected return. So like that. So that's why you see that this hyperbola is kind of well, rotated, because it's rotated like that. Otherwise, it would be something like that. But it's rotated as if we treat risk as a major axis and expected return as a secondary axis. But this is not like that, and therefore, oops, I didn't want this. Okay, that's actually there was about to. I wanted to ask the question about this, but anyway. So we can estimate it for CPM, but how we estimate here of markets for this model? How can we estimate expected return? You mean the expected return of the markets portfolio, or what do you mean? What do you mean expected return of markets? Yes. Okay. Well, we have not talked about this yet. This question will be answered. Actually, that will be just a part of narration in the next slides, and then also in the next lecture as well. So just you have to wait. Anyway, so right now, just what you should understand that each points in this represents just different portfolios And in what terms they are different? They are different in terms of their weights. So essentially, okay, let me just move once again here. So that's what's with Zoom. We finally have found a kind of curve, hyperbola, which represents an inverse dependency of the variance dependency of variance upon expected return due to this substitution. So I would take this formula and substitute it here. So, but our major well, independent variable here is weight. So essentially recall that we express weights in terms of, so we express weights in terms of expected return, and then we just substitute it here. So our major variable is weight. So we just alternate weights, and when we alternate weights, we get different portfolios. Obviously, if we alternate weights, then these portfolios will have different level of variance, different level of standard deviation, and different level of expected return. So obviously, these portfolios will be different in terms of expected return and in terms of their risk. But once again, this all happens just because we alternate weights. And therefore, all our portfolios lie along this parabola, no, not parabola, hyperbola. We cannot just go anywhere aside from this hyperbola, because once again, this is just a function. Like, so we have a function, y is a function of x. So just some mathematical function. In our case, this is a hyperbolic function. But anyway, so this function represents all possible points. You can draw any function and you just cannot go anywhere from this line. So here we have the same. You just cannot go anywhere aside from this line. That just all the possible portfolios lie just along this hyperbola and nowhere else. Now let's look, so this hyperbola is very important and it actually has some labels. Now let's look at these labels and names. So first of all, the whole hyperbola is actually called mean variance frontier. So the whole hyperbola is called mean variance frontier. Now, a very important point here is this one. This is actually the vertex of the hyperbola. In Russian we say вершина, hyperbola. So why this point is very important? Because at this point you actually achieve the minimum possible level of risk. So again, we cannot go any further from this line because this is how this line is constructed using this function. So we just, it's impossible under conditions which you have, this is just not possible to go away from this line. And therefore, even if we really want to have a portfolio which has less risk than this level of risk, we just cannot do this. So this is our minimum variance portfolio. So we just cannot have a portfolio with smaller variance than here. So therefore, this portfolio is very important, and we call it minimum variance portfolio. Again, remember this. And finally, this vertex of the hyperbola divides the whole hyperbola into two parts, the upper parts and the lower parts. So you can see that the lower parts is now highlighted in gray. So gray is something associated with inactivity. So let's call this lower parts inactive, lower sides of the lower half of the hyperbola inactive. Why so? Because even though we do have different portfolios here, but for these portfolios, we can actually find better portfolio. For example, this portfolio, this one, it can be described with this level of risk and with this level of return. But if we read up here, then we find another portfolio which has the same level of risk, but it has higher level of return. Therefore, if you are rational, you will not agree to this portfolio. It doesn't make sense to construct this portfolio. You can construct this portfolio, which will be equally risky, but it will give you a higher return. Therefore, this part, the lower half of hyperbole, is inactive because, it doesn't make sense to form these portfolios. So we're interested only in those portfolios which are highlighted in this purple color, so the upper parts of the hyperbola, because these portfolios are the best portfolios which you can get under the conditions which we have. So this part is called efficient frontier. Efficient meaning that so this half, the gray one, is inefficient and the purple one is efficient. So do not get confused. Mean variance frontier means the whole hyperbola, and efficient frontier means the upper half of the hyperbola. So do not get confused, because sometimes students think that this is the same. No, this is not the same. Okay, that's it about the slides. Now what? Now let's go to the next slide. Okay. And actually, well, the hyperbola which I have drawn here is just one of possible shapes which a hyperbola can take. Actually, hyperbola can take this shape. It can be even more extended like that, or it can actually be quite surrounded. Well, you should understand that hyperbolas, even though they have this standard form, but the degree of extension can be different. And then the question is, how can we determine the shape of the hyperbola? That is, what is the major parameter in our equation, which actually defines whether the hyperbola is rounded like this one, or it is more extended like this one. So which parameter defines the shape, the precise shape of hyperbola? And actually, upon correlation, right, yeah, good that you know this indeed. So actually, this particular shape of hyperbola will be determined by the correlation coefficient. So let me move to this slide. Well, the correlation coefficient is actually is given here, but this is covariance. And I guess you remember from econometrics that covariance, we can draw correlation coefficients from covariance. So this is our correlation coefficients. That's how we can draw it from covariance. And also you all know that correlation coefficient is defined between -1 and 1. So it ranges from -1 to 1. And now what I did here, I just, I constructed this in my Excel. So I just, I use the same data, but just the different correlation coefficients. So here we have 1, and then I slowly decrease correlation coefficients, and now you can perfectly see what happens to hyperbola. When the correlation coefficient is equal to 1, hyperbola degenerates into just a straight line. So that's what we have here. But then when I start decreasing the correlation coefficients, we now see, so here we see a little bit of hyperbola. Here hyperbola looks more like hyperbola, and then it becomes extended, even more extended, and finally when we move to -1, instead of hyperbola, again we have something different. So here the hyperbola is so extended, and the angle now, so here we have still kind of curly, so here for example we have curly parts, but here we have just an angle. So hyperbola turns into two straight lines. So this is just hyperbola, how we can get hyperbola from a straight line, and then how hyperbola goes into two straight lines. Well, generally we can say that when rho is equal to 1, and so when rho is equal to -1, strictly speaking, we do not have a hyperbola. We have either just one straight line, or we have two straight lines. So these are extreme cases, and the other cases are just cases for a hyperbola. So extreme cases, the mathematics for the extreme cases is the same, just shapes are different. But actually, these two extreme cases are very rare. So correlation, when correlation is equal to +1, we have absolute positive or perfect positive correlation between two acids. So recall that we have acids I and acid J. So we have perfect absolute correlation between acids I and acid J. To be more precise, between returns on acids I and on acid J. And as I said, this is very rare because it's really difficult to find such two acids which would have positive, absolute positive correlation. Can you think up of any examples when we have these kinds of positive correlation between two acids? So can you tell me such two acids as an example? Frankly speaking, I don't really know much about crypto assets, but my idea is that they behave just as any other assets. I don't think that they have perfect perfect correlation. They might have nearly perfect correlation for some reasons, for example, but I don't think that their correlation is just strictly equal to 1. They can be equal to, for example, 0.99 or 0.95. Yeah, the same with a stock and I don't know why ETF. So ETF usually, well, there is no ETF on just one stock. So ETF, the basic dandelion portfolio for ETF is index. But even in this case, so absolutely or maximum. No, like even in this case, these are good examples like similar companies or preferreds and non-preferreds. Non-preferreds mean ordinary, preferreds and ordinary. Good examples, but even in this case, you will not get a correlation +1. You can get correlation, for example, again 0.95, but not 1. This is for sure. Like, and for example, you can check it. So take Surgutneftegas, preferred and common stock, not ordinary. I'm sorry, it's not an ordinary stock, it's common stock. So you can check it. Their correlation is not equal to 1. So share and deposit receipt, the same, not 1. Might be very close, but not 1. So can someone tell me an example where we have just +1 correlation? And you know all this example, all of you. So while are you thinking, I will give you an example which you don't know, but think of the example which you know, and I'll give you hints. We studied this example in the bonds in the first half of the course when we discussed bonds. So an example is I'm not sure, but students somehow just tried to convince me that this was true, but probably. So it's about Nokia. So Finnish stock markets and Nokia. So Finnish stock markets meaning their markets index. So Nokia was so dominant some time ago. Nokia was so dominant in the Finnish stock markets index that the index actually moved just exactly like Nokia moved. And so the correlation was +1. But that was just probably, this is a very rare occasion. It means that just the whole market is simply is nearly presented just by only Nokia, meaning that the weights of Nokia, the influence of Nokia on the index was just like nearly 100%. No, not at all. It's just, it's even worse. No, but I have given you an example, not example, a hint. So what did we study in the first half of the course? It's about bonds. So the hint is that not tips. So the hint is that two assets should just move exactly, should have the same direction of movements and the same scale of movements, not just approximate scale of moves, but just the same. So strips, okay, can you expand on this? Nearly correct, but not strips, but what, just strips? Or strips are discount bonds, and obviously if we just look at strips only, I mean at individual strips, then they will not go in the same way as government bonds, because government bonds are coupon bonds and strips are zero coupon bonds. But what we can zoom with strips, and so two industrial index funds, no, again, not like that. So will you give a more exact, more correct answer? So on one hand, we have government bonds, and on the other hand, so the assets should be just identical. Otherwise, they will not. They might have very close correlation, very close to one, but not one. But if we have just identical assets, then indeed they will have perfect absolute correlation. So government bonds and what? So you just only need to add one more word. Not just strips, but okay, a portfolio of strips. Yes, a portfolio of strips. So you need to construct a portfolio of strips which will represent just one particular bond, and then their correlation indeed will be +1. All other assets, in all other cases, when we have similar assets but not identical assets, these cases will never give you correlation equal to +1. So the assets can be very similar to each other, but they will not have an identical they will not have identical moves, so they will not give you a correlation +1. If you want to have correlation +1, then this asset should be absolutely identical, in a sense that you have one asset and you have its synthetic replication. So we have coupon bonds and we have its synthetic replication, a portfolio of strips. So also we can actually synthetically replicate what we can synthetically replicate a call option. So how do we replicate a call option? If you just know by chance, I'm not sure about this. Okay. A call option can be replicated by an energy line stock, and what is this? And not really opposite deals, but you need to take a certain position, a long position in a stock, in a certain amount, obviously, certain amounts, meaning with this, this delta ratio, and then also a corresponding position in cash. Actually, you can synthetically replicate some using options. You can actually synthetically replicate some other assets as well. So this example, portfolio of strips and the government bonds, is not a single example. So you can actually think of other examples as well, where the assets will be identical and then they will have the same correlation. But now let's me ask about this one. So correlation -1, just another an opposite case, or the opposite case. Can you think of an example where we have absolute negative correlation? Yeah, cash stock. But actually, this is really easy. Okay, let's talk about again this portfolio strips and coupon bonds. How can we achieve a absolute negative correlation in this case? Yes, exactly. So if in two long positions they give you perfect positive correlation, then just you need to short one of the assets and then you will achieve a perfect negative correlation. Anyway, having such assets is a very good thing because this allows you to hedge, which is just, as you know, a part of any arbitrage situation. And so this is that's why we can achieve arbitrage in the coupon bonds markets when we have strips, if this market trades strips. Okay, so anyway, that's it about these slides. Now let's move further. And again, we have this hyperbola. And recall that this gray part is inactive. Here we have minimum variance portfolio, the minimum risky portfolio in our situation. Now let's introduce some points here into this hyperbola. So, for example, let's assume that this is a portfolio, and let's assume that in this portfolio we have the following weights. So recall that we only have two risky assets, I and J. So assume that, and then difference points in this hyperbola represents just portfolios with the different weights. Obviously, there might be such a portfolio where all the weights is given only to risky assets I. So here we have such situation that we have 100% of risky assets I, and then there will be only 0% for risky asset J. Now let's introduce another portfolio, which is just the opposite to this portfolio. And now we have 0% for risky assets I, and then all the weights will be given to risky asset J. This situation is quite straightforward. So obviously, we see that risky assets I have more risk, right? Because this level of risk here we have risk for assets J, and here we have risk for assets. And this is risk for assets I, so sigma I, and this is risk for assets J. So obviously, if risk for assets I is larger, then the expected return from assets I should also be larger than here. Well, this is quite straightforward. However, obviously, we can find some weird assets where risk is larger and the return is still lower. But generally, the situation is that as risk increases, expected return should also increase. So that's why we just have these kinds of position for portfolio I and portfolio J. So portfolio I lies to the right and upper to the compared to to the upper compared to SJ. So this is just because of the risk and the return combination. Now let's me just remove these lines because they will bother us. Okay, and so the rest of the points in this hyperbola will simply represent all other portfolios with all different combinations of assets I and asset J. That is all different weights. But essentially, so as we move like that, we gradually decrease the weights for asset J. So here it has 100%. So as we move here, we gradually decrease the weights given to asset J and gradually increase the weights of assets I. And then we move further like that. And then again, the weights given to asset J decreases even further, and weights given to assets I increases even further, and then we reach this portfolio where weights of assets I reaches 100%. So from zero in these points, we have weights given weights increases from 0 to 100% as we move from these points to these points. Okay, let's me once again remove these lines. Okay, now I guess you understand how these points are formed. And let's look at other points. So if, for example, we have a points here, so one possible portfolio, we can say that in this portfolio, we have obviously a combination of weights. So some weights given to asset J, because in these points, asset J has weights 0, but if we have not reached these points yet, so we're at these points, and therefore asset J still has some positive weights here. And then also assets I also has some positive weights. So here we have positive weights both for asset J and assets I. Now at these points, once again, asset J has 0 weights and assets I has all the weights. But now we move even further to the left, to the right, I'm sorry. And then we reach this portfolio. Will you tell me what weights do we have in this portfolio? And this is my question to you. Right, exactly. So obviously, if here we have 100% of assets I, then if we move further to the right, we increase even more the weights of assets I, so more than 100%. But then the question is, how can we increase the weights? We don't have more money, so all our money is already given to a risky assets I. So a natural answer is like Konstantin offers. So we need to short sell asset J. So asset J here at this point, asset J has 0 weights, but then as we move further to the left, asset J weights decreases even further from 0 to negative area. So it becomes negative, meaning that we short sell asset J, and then we take the proceeds from short sell and take these proceeds and buy more assets I. Okay, good that you understand this. Let's once again remove these redundant lines. Okay, and now let's see what we have here further. Probably, well, let me first switch on marker. Yeah, I just okay. So here we have marker. Yes, and then the question is, so we know that we obviously have just different portfolios here, but the most important question is, if you are an asset manager and you have a client, how do you understand that which of these portfolios, which of these possible portfolios will suit your clients? So recall that what I said last lecture, that we have something like coefficients of relative risk aversion CRA. So CRA, and then we also have coefficients of absolute risk aversion, CARA. But anyway, so you, as an asset manager, you need to know the degree of risk aversion of your clients. So if you just don't know this, then you have no right to form a portfolio for your clients, because the risk, the level of risk of this portfolio might not be in line with the level of risk of your clients. So if you do this, if you form a portfolio for your clients without first revealing his degree of risk aversion, you will be fired. Probably even your company will have to pay a fine. So and that's the most important question is, how do you understand that this particular portfolio is in line in level of risk? It is in line with the risk aversion of your clients. Well, recall these nice lines. So these lines represent indifference curves of your clients. So we'll get it here. Okay, we'll get it here. So these are, once again, these are utility functions. So recall that we actually can reveal the degree of risk aversion from a utility function, because CARA and SCRA are simply a ratio of second order derivative to the first order derivative of the utility function. So therefore, we can draw the degree of risk aversion from the utility function. And these are indifference curves, which corresponds a utility function. So this blue light blue curve is less conservative investor. This dark blue curve represents a more conservative investor, because you see, as we increase the degree of risk, a very conservative investor would require much more compensation than some less conservative investor, because for this case, we can increase also the level of risk, but the investor will ask for smaller compensation. So because this the second curve is not as steep as the first curve. So this light blue line is less conservative, risk averse, but less conservative, and dark blue line is risk averse but much more conservative. Well, recall that, for example, CRA is like that. So initial level of wealth, second order derivative, first order derivative, and also do not forget that we'll actually need to put minus here. Well, this is a good question, because if you just look, by the way, there's one A here, CRA. So if you look at this, a natural question is that in order to calculate SCRA, we need to find out the utility function of an investor. Otherwise, how? Well, you need to know the precise mathematical formula which describes the utility function. Then you will take the first order derivative from this formula, second order derivative, and then you calculate CRA. But in fact, no one does it in practice. In fact, they just try to find, this is actually a number. So recall that what we discussed last time. This is just a number, by the way. It ranges from 2 and, as far as I remember, 8. So the closer to 2, so the more conservative the investor is, and the closer to 8, the less conservative the investor is. So actually, it's easier to find the number than to estimate the utility function, and then estimate the first order and second order derivative. So usually, asset managers find the number. And how they find it, well, there might be different ways to do this, from very primitive ways, like that was in my case, with my broker to some more complicated cases, but in this case there will be more precise cases, and then with some experimental works, but probably you can get the best approximation, the best estimates of it. So it just depends on an asset manager. It depends on and it depends on your degree of well, customization. If you are very rich, wealthy customer, then probably you will have a larger degree of customization, and you will an asset manager will try to be more or less precise in finding your CRA, but not like not as in my case. We will talk about this also a little bit later. Anyway, so let's just take this indifference curves and superimpose them onto our graph. Where is our graph? Okay. These are our graphs. This is our graph, and then so we have done superimposition, and now you see what's now you can actually understand how to see at least graphically about how what I'm doing now. I'm just explain to you this graphically. When I switch to the master's narration, I will just show you how it's done using formulas, and then we will have example using numbers. Well, a real life example, but this is just you know a bachelor narration. I will just use pictures here. And so indifference curves are something very subjective, which describes a particular investor. And then you see that, for example, this light blue curve represents less conservative investor, and this dark blue curve represents more conservative investor. So we just need to find the points of tangency between these portfolios and indifference curves, because both these curves, indifference curves and hyperbola, are presented in the same plane, the plane which is measured with expected return and standard deviation. So therefore, that's why we can make this superimposition, because they have the same axis, the same measurements for axis. So, and therefore, that's how you essentially find, that's how you understand that the portfolio which you have created is in line with the level of risk of your investor, because we have this point of tangency with indifference curves. And indeed, so this less conservative investor whose indifference curves is more extended, we can, for example, find a point of tangency here. And this portfolio, recall that this portfolio suggests short selling, which is actually quite risky. Therefore, indeed, this light blue investor is less conservative, because he is okay, he's ready to tolerate short selling. And this dark blue investor is very conservative, and obviously he would a natural solution for him is this portfolio which contains only positive weights, that is only long positions. And if we have very conservative investor, then like the most conservative investor, then we would choose this portfolio for him, because this portfolio is the safest one. It's not safe, in fact, because it has positive level of risk, but in our conditions, this portfolio is the safest one. Anyway, so what did I write here? Depending on his subjective preferences. Well, this is what I have already explained. So this choice is subjective, meaning that you have to understand the degree of risk preference of your investor before you create a portfolio for the investor. And then also, that's what I said, the most conservative investor will choose minimum variance portfolio. Actually, you will choose, if you're an asset manager, you will choose the minimum variance portfolio for your most conservative investor. Okay, now that's all is fine. However, there is something which is missing here, and this is the risk-free rate. In most cases, though actually not always, but in most cases, risk-free rates is available for investments as well. And recall that all this, what we have discussed previously, it was all about too risky assets. But probably let's be more realistic and let's assume that there is also risk-free assets which is available for investments, and let's introduce these risk-free assets. So I will move to the next slide. Just the same, so the same hyperbola, nothing changes here. So this hyperbola represents all possible combinations of two risky assets. So these portfolios, any points on this hyperbola represents a combination of two risky assets. It just does not contain a risk-free assets. But now let's introduce also let's introduce a portfolio which now consists only of risk-free assets. So it contains nothing else, just only risk-free assets. That will also be a point, just like here we have a points, and this portfolio will also have a that will be a points on this graph. And now you please tell me, where should I place these points? Where should I locate these points on this graph? Right, risk-free assets has no risk, so it will be located, if it has zero risk, right, it will be located on the y-axis. Okay, let me locate it here, for example. Can I do this? Why no? So bigger than the area of global minimum, should be on the level of minimum risk portfolio and the efficient finance. Well, right, so it's not that it should be on the level, it should be actually below the level. So I already know that here we have certain amounts of risk, and let me remove this. Okay, so here we have certain amounts of risk, and we have a corresponding expected return to this level of risk. So if there is no risk, then we just cannot have higher return. It should be somewhere here. Anywhere, it depends on the state of the economy, but anyway, it cannot exceed this level of expected return. I have just explained. Did you understand it? No. So this is our minimum minimum variance portfolio. So that's what we discussed. So this minimum variance portfolio offers this level of risk. So so this level, not this level of risk, this level of return. So this level of return is associated with some positive, probably not big, but some positive risk. So if you have an asset which is not associated with risk at all, it cannot have this high return, and moreover, so it cannot have any higher return. It should have a lower return. Do you understand that? Otherwise, what sense? No one would invest into the minimum variance portfolio in this case. Everyone would invest into risk-free assets, but then there will be just again a mess. Okay, so I will just remove all this. So Okay, so I put risk-free return somewhere here. So this is also this is just a point. So this is a portfolio, and this portfolio consists of 100% of risk-free assets and 0% of risky assets. So just only risk-free assets in this portfolio. And now what we do? We take array Luch in Russian. So we take array and uh, draw it in such a way that it starts from this portfolio, from RF, from these points, and it should be tangent to the hyperbola. So I think the points of tangency is somewhere. Okay, so this is our points of tangency. So obviously this portfolio, so okay, this points also represents a certain portfolio. And let's call this portfolio, first of all, tangency, because the name is obvious, because we have a point of tangency here. So one name for this portfolio is tangency portfolio. But this tangency portfolio has also another name, and this another name is optimal portfolio. And now my question to you, why do we call it optimal portfolio? Well, you understand why we call it tangency portfolio. Why do we call it also optimal portfolio? You know, this alternative name. Why do we call it optimal? So this is my question to you. So while you are thinking, I will also tell you that, as you can see, this portfolio lies on the efficient frontier, right? So this portfolio is efficient, so we can call it efficient portfolio, but we have many efficient portfolios on the efficient frontier. So any portfolio here will be efficient, but there will be only one portfolio which is not just efficient, but it's also optimal. Mathematically, mathematically what? Um, yes. No, it's not that it's optimal for there is well, it's optimal. No, not actually. I insist on this adjective optimal. We should not use this adjective too frequently, because this optimal is a certain, well, this adjective optimal suggests that, how to say this, suggests that it's um, well, it's actually have a very precise meaning, optimal, um, because optimal means that well, this precise meaning means that we solve optimization problem, and when we solve optimization problem, we get something optimal, we get optimal solution. So that's why I think in real life we quite frequently use the adjective optimal without bearing in mind that this actually means the solution to the optimization problem. For example, we can say optimal weather conditions. But in this particular case, actually optimal means that we have a solution to the optimization problem. That's why we have optimal. Okay, so yeah, this is about Sharpe ratio. And now also Sergey writes, because it's minimized the risk for the same return. Minimize the risk for the same return as the risk-free assets. Well, no. This is something weird. Okay. So let's me just finish in a couple of minutes before we have a break, but let's just discuss this optimal. So optimal means that this portfolio is a solution to the optimization problem. And now my question is, what kinds of optimization problem are we trying to solve here? Minimum risk, maximum return. Yeah, this is just, so standard students' mistake. I think each time when I ask this question, there's also students who make this mistake. Classical mistake, I would say. Okay, that sounds better, though I don't understand what you do mean when you say suffer. Every unit suffer. So who is suffering here? Higher return on 1 unit of risk. Yeah, that's better. Yeah, that's better. So yes, this is Sharpe ratio, but I just want you to understand what is behind the Sharpe ratio. Yeah, I understand, Zhao. I don't understand why you use the verb suffer. So who's suffering? Who's going to suffer here? Anyway, so let's look at these points. So essentially, these points, it lies both on the efficient parameter, but also it lies on this straight line. So it just shares these two curves, straight line and the hyperbola share the same points. And therefore, we also can say that since this is the point of tangency, we can say that this straight line is tangent. And you know the property of tangency. So we can say that this line represents the slope of this for this curve. And how do we find slope? I guess you understand that the slope is just a ratio of this distance to this distance. Right. So, and this distance, this one, what is this? This is simply the expected return on the tangency portfolio. Okay, let me call it now optimal portfolio minus risk-free rate, right? And this distance is simply the level of risk of our optimal portfolio, so standard deviation of our optimal portfolio. Indeed, this is called Sharpe ratio. And now just for you to understand that some students, just as it was said before, say that here we try to maximize, by the way, this is. So what we have in the numerator is actually risk premium. I guess you'll understand this, risk-free rates. So this is our expected risk premium. Risk premium, let's write like that, risk premium. And so so some students say that we try to maximize expected risk premium while having minimum standard deviation. No, this is not. Let's just assume that, for example, here we have 10% of a risk premium. I'll just use some numbers, and we have 20% of standard deviation. And then the ratio is going to be equal to 0.5. So how we can interpret this? So if for 20% standard deviation we have 10% risk premium, then we can actually write it like that. Then for 1% standard deviation, we have 0.5% risk premium. So we can say, so 1% standard deviation means 1 unit of risk. So it's not that we have minimum risk and maximum premium. No, it says that we take at these points, we have the biggest premium relative to 1 unit of risk. So once again, we achieve maximum possible compensation for taking relative to 1 unit of standard deviation, not just minimum level of standard deviation or something like that. It's just like for 1 unit of standard deviation, at this point, we achieve the maximum possible compensation in our portfolio. So this is obviously, if we achieve maximum compensation for 1 unit of risk, this is obviously the solution to the maximization problem. And the maximization problem is one type of the optimization problem, and therefore that's what we have. That's why we call it tangency portfolio, or let me just write it also like that. This is our optimal portfolio, a solution to the optimization problem. Okay, now let's make a break for about 10 minutes, and then we will continue with this, and then we will switch to the master's level. But this is the last slide for this bachelor level. Okay, so that's it for today. Now I'll stop the presentation, the demonstration, and we will have a break.
Коллеги,
Okay, so shall we start the other parts of the lecture? And by the way, where's the presentation itself? Let me switch it on once again. Well, so this is the last slide for this topic at the bachelor level. What we still have missed here is that is our investor. So we already know that this point of tangency is featured, represents a portfolio which is optimal from the point of view of compensation for 1 unit of risk. However, it does not mean that this is the best portfolio, because meaning that this is the portfolio which suits all investors, because as you know, different investors are featured with different level of risk aversion. Therefore, even though this portfolio is optimal, it does not mean that all investors will choose this portfolio. In fact, in order to find out the portfolios which are chosen by our investors, we again need to apply in different curves, just as we did it here. So here we're applying different curves. However, now you can see a very drastic difference. So compare in this slide, we do not have, we still have not introduced a risk-free assets, and therefore we try to find a point of tangency with between the efficient frontier and the indifference curves. But now we have introduced a point of we have introduced a risk-free asset, so we have one more portfolio, and now what we are going to find, we also are going to superimpose indifference curves, but now we will try to find a point of tangency not with the hyperbola as in the previous case, but point of tangency with this straight line. Why so? Because once again, look here. We try to find points of tangency with the hyperbola because we know that all portfolios lie on the hyperbola. We don't have any portfolio here, we don't have any portfolio here, so all our portfolios form a hyperbola. It just depends on what weights for each asset we choose. But now, what we can actually do, so also we can actually do the same. We can try to find a point of tangency like that, for example. But look here, we have this optimal portfolio. It lies on one hand, it lies on the hyperbola, but this is a point of tangency, so it actually also lies on this straight line as well. Actually, this straight line is formed by connecting these 2 points. These points are F and points T. So if we connect these 2 points, we will get a straight line. So what it means, let's look at these points once again. At these points, we have risk-free portfolio only. So 100% is given to risk-free assets and 0% is given to risky assets. Now let's look at this optimal portfolio. Here, this optimal portfolio consists only of risky assets. It does not contain any risk-free assets. Why so? Because actually it lies on the hyperbola. And recall that hyperbola consists only is formed by portfolios which consist only of risky assets. So therefore, we can say that here we have 0% of risk-free assets, and here we have 100% of all of our 2 risky assets. And now you can see what actually we obtain when we have this line. So this line represents different points. So different points. And these different points are also portfolios, just they contain different weights for the risk-free portfolio and for the tangency portfolio. So when we mix weights for the tangency portfolio and risk-free portfolio, we we appear somewhere here. And so all these points, or this line essentially represents a kind of mixed portfolio, which contains on one hand on the risk-free assets and on another hand of the tangency portfolio. And these weights will be positive, obviously. But if we go to the left of the tangency portfolio, then that also will be a mix of the risk-free portfolio and the tangency portfolio. However, this time, this mix will contain both negative weights and positive weights. So if here we have 100% of the tangency portfolio, then if we go to the left, oh, I'm sorry, if we go to the right, I'm saying left always, should be right actually. So if we go to the right, we actually increase the weights of the tangency portfolio to more than 100%. How can we increase these weights? Again, we have such an amount of money, we just cannot add more money because we have certain budget restriction. We cannot just add more money. So then the question is, how do we increase the weights of the tangency portfolio? Well, we need to short sell risk-free assets, and then we use the proceeds in order to increase the weights of the tangency portfolio. So, for example, somewhere at these points, we will have more than 100. So we have, so we start with the risk-free. So we have negative weights for the risk-free portfolio. Well, it will be negative. And we will have more than 100% weights for the tangency portfolio. Anyway, you see what happens. Actually, we still can stay on the efficient frontier, not a problem. You can choose actually any portfolio here. But if we just only combine two portfolios, the tangency portfolio and the risk-free portfolio, we can actually achieve a better solution because we shift from this curve to this straight line. We actually go in the so you can see we go in the northwest direction. So northwest meaning here. So this is our northwest. So we go in the northwest direction. So we actually go to we shift to a higher line. That is with this higher line, for example, we have and just compare these points and these points. We have the same level of risk, but here in these points we have a higher return. So we can say that we form another one more efficient frontier, which is better. It's better because for the same level of risk, it offers us higher return. And at these sites here, it's also better because actually now, for example, for this level of risk, we have higher return, but we actually additionally get more options. If you are very, very risk averse, you do not need to choose this minimum variance portfolio. You can actually choose a risk-free portfolio, so you have more options now. So this is definitely good. So as you can see, the introduction of the risk-free assets essentially increases our our position, increases the positions of our investors. We can offer them better portfolios. And in order to offer them better portfolios, we only need to find the tangency portfolio, and also we need to have the risk-free portfolio. That's it. We don't care anymore about these portfolios which are located on the hyperbola, on the efficient frontier of the hyperbola. What it means? It means that we don't need to think what weight do we need to give risky assets. We only need to find weights for one risky portfolio, tangency portfolio. As long as you find weights for the tangency portfolio, that's it. You don't need to think about any other combinations of risky portfolio. You manipulate only with the tangency portfolio. So you just combine the tangency portfolio and the risk-free rates. Let me remove some lines here because they will bother us. Okay, this one, this one. And then the rest of the procedure is the same. You just superimpose in different curves as usual. So for example, we have 2 points here. Once again, this points involves short selling. These points, it does not involve short selling. I want to remove this also. So we have 2 points. 1 point represents most safer portfolio. Another point represents riskier portfolio. And now we simply superimpose in different curves. Well, obviously, since you are as a retail customer cannot issue bonds, you could actually issue bonds, high quality bonds. That would also be something like short selling because you essentially take credits, but you cannot do this because I don't think that Konstantin Garilov can issue bonds, moreover, which has triple A credit rating. So the only thing which you can do is just to try to take yeah, I guess so. At least no one. If I don't think that you will be able to convince your colleagues that you can to ask them to buy bonds and convince them that your bonds are high quality, uh, high have high credit quality. So therefore, the only thing which is accessible for you is just to take credits. So short sell in this case means taking credits. Okay, so let's superimpose in different curves. And now you can see, so we can actually superimpose our indifference curves now lie higher than previous indifference curves. So you can see, so this indifference curves is taken from our previous slides. And now we actually have another blue, light blue indifference curves. You can see that actually we go a little bit higher. We go to this indifference curves, which is higher, so which is better actually. So the introduction of the risk-free asset actually significantly improves the situation for your clients if you're an asset manager. So that's how it looks like, and let me just summarize it like that. A choice of the portfolio. So if you're an asset manager and if you want to use the portfolio theory in order to form an assets, a portfolio for your clients, then this is essentially a two-stage process. So you operate within two-stage process. The first stage, you need to find two portfolios, tangency portfolio and a risk-free portfolio. Well, risk-free portfolio, I guess you don't need to find it. It's I think it's very obvious whether which risk-free portfolio is available in the market. So you essentially only need to find the tangency portfolio, and recall that the tangency portfolio is found by solving the optimization problem. And then so this is the first stage. This first stage is, well, I call it objective because in this first stage, you do not think about a risk preference of your investor. You find two portfolios which will be used for all investors. The combination of these two portfolios for different investors will be different. But at the first stage, you just find these two portfolios, and this finding of these two portfolios is independent of the risk preference of your clients. So this is an objective stage. You just find two portfolios, and then you shift to the second stage, which is subjective, because in this second stage you try to compare the try to determine the risk preference of your investor, and then combine the tangency portfolio and the risk-free portfolio in such a way that this portfolio will be in line with the risk preference of your client. So this is something which I call subjective stage. So two-stage process, objective stage and subjective stage. So that's it for the bachelor level narration. Do you have any questions? Okay, looks like you do not. Good. Now I'm going to switch on another presentation, and that will be the same theory, the portfolio theory, but now it will be at the master's level. So I need to stop this demonstration now and turn on the master's level presentation. Okay. Okay, now you should see it. So are you psychologically prepared for for this kind of master's level narration? Okay, so silence means that you're prepared. Okay. Well, this slide, I think this slide is not important, so we can miss it. Okay, so let's start with this slide. Well, let me switch on the marker. So again, we assume that you are an asset manager, you have a client, and the client is going to invest certain amounts of money. So recall that wealth is denoted as W, and so zero means that right now, at this point of time, the investor has certain amounts of money for investments, and then the question is, so now you don't have just only two risky assets, so you have risk-free assets and you have many risky assets, just as usually the case in stock markets, in financial markets. So you have, for example, government or treasury bonds, and then you have many stocks. And so there is this problem, the problem of portfolio choice. You need to find out weights which you will give to risky assets and to the risk-free assets. And so that's the major problem, how to understand, how to determine which weights is going to be given to each assets, risk-free and risky. So how to find these correct weights, and it's even a deeper question, what is a correct weight, what is the right weight given to each asset. And then let's try to answer, first of all, this conceptual question. What criteria we choose in order to understand whether this weight is right weight or it's not right, it's not correct weight. That is, how do we define right weight or not right weight? Here's the answer. So we can try to find weights in such a way that the utility of our investor is going to be maximized. Well, why not? After all, this is very straightforward. Each investor has certain points of certain level of satiation from having money. So let's just maximize this satiation. Let's find weights for each asset, and let's construct a portfolio in such a way that the amount of money which will be given at the end of the investment periods, which will be obtained from this portfolio at the end of the investment periods, will be such that the satiation, the utility of our investor will be maximized. So this is actually very straightforward, though it was not like that in the past. I mean, it has all, I mean, well, okay, this is the criteria which is chosen by Harry Markowitz, the one who actually the founding father of the portfolio theory. However, there must be a question. We try to maximize the utility. So this one means end of period. So 0 means the beginning of the period, and 1 means that this is the end of the investment period. So this is the wealth which you will get at the end of the investment period. So we maximize minded that we maximize the utility of the end of period wealth. We do not maximize the end of period wealth. That is, we do not maximize the amount of money which you will get from the portfolio. We will maximize the utility from the money which you will get from the portfolio. And this is also a kind of very important thing, but that is not due to Harry Marcus. That was this is an earlier observation. Actually, that is actually the observation is that we think not in terms of money. We actually think in terms of our satisfaction from money. This is actually different psychologically. So we don't maximize the amount of money, we maximize our satisfaction from money. And if you're interested in this, because I'm not going to develop, amplify this topic, but if you're interested in this, you can actually read about something which is called St. Petersburg paradox. Probably have heard about it. So once again, St. Petersburg paradox, which can be explained from the point of view that indeed this is a psychological feature of people. So we have talked a lot about psychological features of people. Recall that we talked about time and patience, but now we talked about another psychological feature that people think not in terms of money, but not in terms of quantity of money, but think in terms of the satisfaction that they get from money. So therefore, we maximize utility from the end of period wealth. We don't maximize the end of period wealth, so we maximize the utility. So we need to construct the portfolio, meaning we need to find weights in such a way that we will maximize the utility. But also recall that this is going to be end of period wealth, because this will be the results of the investments. And right now, at the beginning of the periods, we simply don't know the results of the investment. This is a random variable. We don't know right now the results of the investments. Therefore, strictly speaking, we cannot maximize the utility of the end of period wealth because we don't know what utility will be received at the end of the periods. Well, not received. Okay, let's say you received, though probably the verb is not correct here. So we cannot maximize this. We cannot maximize what we don't know. Therefore, we can maximize what we know. We are going to maximize the expected utility. So we don't know the utility of the end of period wealth, but right now we know the expected utility because we always can calculate expectation. So we are going to maximize the expected utility of the end of period wealth. So that's all is fine. And now I'm going to highlight these major insights which was given by Harry Markowitz, in a sense that this is a really huge, breakthrough in the finance science, because he actually revolutionized, if it's possible to say so, the whole asset management industry. And now I hope you will understand why. So assume that we have this task. We need to maximize the expected utility of our investor, expected utility of the end of period wealth of our investor. But in order to maximize the utility, in order to maximize the expected utility, you need to take the expectation of the utility. In order to take the expectation of the utility, you need to know the utility function itself. So you need, if you want to take the expectation of some formula, you need to know the formula. Therefore, you need to know the formula for the utility function. Now, recall that in our 2 tutorials ago, we discussed 3 possible utility functions. We discussed 3 possible formulas which might describe the utility function: hyperbolic version, quadratic function, and negative log function. Oh, I'm sorry, not negative log, negative exponential function. And then we rank them from the best to the worst. So now you know at least 3 possible mathematical formulas which can describe the utility function. In fact, if you look at the utility function, recall that the utility function should be should have a concave form like that. In fact, we can think of really many versions of mathematical formulas which when um, when represented graphically have this form. For example, again, was let me remove it. For example, the log function, natural log. I think we consider this function as an example in one of our lecture. So log function also has this form, so why not to take this one? Additionally, square, not square, square roots. So y is equal to square roots of x also has this form. So we can think of many utility functions, many versions of the mathematical formulas which will give you the same shape. And then the thing is that there is no standardized utility function because people are different. People are so much different, then the utility function for each person might be described by different shapes. So there is no standardized version to describe the utility function of an investor. So what it means, and moreover, people don't know what mathematical formula describes their utility function. So, for example, you all now know that you do have a utility function. You know that, well, if you believe that you are risk-averse investor, you know that your utility function will be described like that. But if I ask you, do you know the precise mathematical formula which describes your utility function? You definitely say no, you don't know, and that's the major problem. If we um, if we had to find out the personal mathematical formula for each client, then that would just destroy the asset management industry completely, because finding the precise mathematical formula is extremely difficult. It's time consuming and obviously it's money consuming. So now imagine if an asset manager had to do this, then he would definitely ask more money for his services. So the asset management services would have become more expensive, and then probably the asset management industry just would disappear. So essentially, the fact that the asset management industry functions the way it functions now is due to Harry Markowitz, because he said something like that. There is no need to find out individual utility functions for each investor because the expected utility function can be represented as another function which has quite standardized form. So now let's look at this. So what he says, don't maximize this unknown, unobservable personal utility function for each investor. Try to maximize another function, an alternative function. And this function, so what I just write here, this function is going to be some very simple linear combination. And this linear combination will contain expected ends of periods wealth. So this is our expected ends of periods wealth. And also it will contain variance of ends of periods wealth. So we will get a function which contains expectation of the end of periods wealth and variance of the end of periods wealth. And so instead of maximizing the utility function which you first need to find for your clients, which is very time consuming and it's very complicated task. Sometimes actually it's done, but it's done mostly for theoretical interest. In practice, this is not done because this is just very ineffective or inefficient, or both ineffective and inefficient. So instead of this, you can maximize this simple combination of expectation and variance, because actually maximizing this function is much easier. And moreover, this function, this one, it's standardized function, meaning that whatever clients you have, you can always maximize just this function. Okay, that's what he offered, and that's actually what gave the shape for the modern asset management industry. Now, our task now is just to show that indeed we can do this, because then there is a question: can we actually do this? What reasons do we have to replace this unobservable utility function with this standardized linear combination of expectation of the end of period wealth and variance of the end of period wealth? So we need to show that we can safely perform this substitution and nothing will change, because if there are changes, then it's not possible. So now let's show that we indeed can do this. So we just follow Harry Markowitz now. So we're going to prove that this function expected utility of the end of period wealth can be safely replaced by a linear combination of the expectation of the end of period wealth and variance of the end of period wealth. So for this, we are going to involve mathematics as usual. And moreover, we are going to involve our frequently met mathematical tool, second order Taylor series approximation. So now I guess you all remember how the second order Taylor series approximation looks like. So I'm not going to write the general formula. So I already write the result of this approximation. So what we are going to approximate? So we are going to approximate this from this function, utility of the end of period wealth, about what points we are going to approximate about these points. So this is our second order Taylor series approximation. That is the already result of the second order Taylor series approximation. Now, recall that it's just not possible to maximize the utility of the end of period wealth because we don't know what will happen in the future. So we actually, our task is to maximize the expectation of the utility of the end of period wealth. Therefore, let's take expectation of the right-hand side. Actually, this is going to be left-hand side of the equation and also right-hand side of the equation too. So we take expectations of the both sides and then we get the following. So here we have now expectation of the utility of the ends of period wealth. Just for those students who still believe that, I mean, someone asked me about this. There is no difference between curly brackets and square brackets. It's just for convenience because I don't like when there are many square brackets or many curly brackets. So that's why I use just different brackets. Now let's take expectation of the right hand side as well. Mind it that when I take expectation, and you know that expectation is a linear operator. So therefore expectation of the sum, and we have three terms in the sum. So first term, second term, and the third term. So expectation of the sum is equal to the sum of expectations. So we take expectation of the first term, of the second term, and of the third term. And look here, actually the first term, when we take expectation, it stays unchanged. And here is my question to you. Why do you think the first term is unchanged when we take expectation of it? So can someone say, answer this question? Right. Right, so this variable is known to us at the beginning of the period, so we already know how much money we are going to invest, and therefore it's possible to calculate utility of this. Therefore, it's a constant, and the expectation of the constant is just the constant itself, so it's unchanged. Now, we take expectation of this as well. Well, actually, that's what I write here, expectation of this term, and then we also take expectation of this term. Now let's move to this line now. So this is the same. So now, if we want to take expectation here, we see that W0 is our initial value, which is known to us. Utility of the initial value is also known to us, and its first order derivative can be calculated. So this is also constant. And the only random variable is our end of period value. So we can take expectation of it, but as for the rest of the terms, it's just the same, no change. Now let's look at this term. Here we have actually square. So we have expectation of the squared term. This is not as simple as it might seem because we have expectation of this squared term. Therefore, what you are going to do, you can try it at home. So you can open the brackets, not open the brackets, how it's called. I don't even remember how to say it in Russian. Not open the brackets, but some. Can you help me? How do we say this? Сумма квадрата, квадрат суммы, квадрат разности. Раскладываем на квадрат разности. Thanks. So do you know how to say this in English? It might seem simple, but I don't remember. But anyway, I guess those students who do not speak Russian, you understand this. So we just manipulate with this. And then when you manipulate with this, you will get something like the expectation of the squared term, and then you will also get a squared expectation. And now actually what you can do, I think, well, you probably should remember this from econometrics, but if you don't, just look at Wikipedia. There might be some, you should find this connection between variance and expectation. So expectation and variance are connected, but there is a formula which connects the variance and expectation. And then when you take this, well, I will just translate this literally. So when you take the square of this difference, you will find these terms, and then you actually can obtain variance. Okay, this is actually what we have here. So this is the formula which you should employ. So if you employ this formula, then you will find that you have actually variance here. And okay, and this is, that's what we have in this line, So now let's look at this line. First of all, you already see that, recall that what our aim is, we need to represent some unobservable utility function, which is different from difference in vectors. So we need to replace this function with a standard combination of expectation of the end of period wealth and variance of the end of period wealth. And you already see that we are halfway here. We are on the way here because we already have got expectation of the end of period wealth and variance of the end of period wealth. So actually we already can say that this expression looks like some functional form, some linear combination of expectation and variance. The only thing is that we have much more terms here. I wouldn't say that this is a standardized and simple combination. So, well, mathematically, this combination is indeed simple. We have only plus and minus here, and also we have square here. Well, this is simple, but this is a long expression. Let's try to simplify it even more. So let's just try to achieve an expression where we only have expectation and variance and nothing else. So how to do this? Obviously, well, let me just write it here as well. Utility, end of period wealth. Well, obviously, if we want to manipulate with the left-hand side of the equation, we have to manipulate with the right-hand side of the equation too. Otherwise, it will be an unfair manipulation. So if we want to keep this approximation sign here, then if we want to make some manipulation with the right hand side, we need to do the same manipulation with the left hand side. But we want to have the left hand sides unchanged, because that's what we want to achieve. We want to substitute this unknown expected utility function with a standardized combination of expectation and variance. So we want to keep the left hand side unchanged. So how to simplify the right-hand side if we want to keep the left-hand side unchanged? Simple mathematical manipulation will just not work here. So what to do? In order to go further, we're going to employ the results of one theorem. I'm not going to show you this theorem or its proof. I'm just going to show you the results. For this, let me move to the next slide. So this is our problem. So we want to maximize the expected utility function. Originally, we want to maximize the expected utility function, but as a final result, we want to substitute the expected utility function with a linear combination of expectation and variance, and we are going to maximize this function because it's simpler and it's standardized for all investors. But now this function, this linear combination, looks clumsy. We would like just to simplify it. And in order to simplify it, we are going to employ these results. So this is optimization theory. Probably some of you who studied the optimization probably know this theorem. So the theorem states like that: the optimal values of an optimization problem are not affected by a monotonic transform of the optimans. So optimans is something in Russian we say целевая функция. I think probably in English we can say objective function, but also this is optimand. So this is our optimands. This is what we are going to maximize, right? So we're going to maximize the substitutes of the expected utility function. So this is our objective function, optimands, or in Russian целевая функция. And now once again, let me just say it once again. If we perform a monotonic transformation of the objective function, the function will look differently, but the results of the optimization will not change. It will be the same as for the original objective function. And this is really a great result because now we can manipulate with the right-hand sides only, and we can do it safely. We know that we will obtain the same results. However, mind is that we have a restriction. It's not just any kind of manipulation which we would like to perform. We can only perform a monotonic transform. So monotonic transformation. So do we have here those students who knows mathematics well? Can you tell me what is monotonic transformation? Yes, but what is meant by a monotonic transformation? So we need to use some very flat constants. Thin constants will not work, only fat constants. Okay, well, yeah, I understand. Okay, constants. So indeed, we can use constants, but let's actually use an example so that you could understand where we have monotonic transformation and when a transformation is not monotonic. I will just use very simple function, not like that. I will use a very simple function. Y is equal to x. So just the simplest function possible. Now assume that I have assigned certain values for x, 1, 2, and 3. And then we can calculate values for y. That's going to be also 1, 2, and 3. Okay, Now, let me apply one transformation to this function, and this transformation looks like that. I multiply x by 2, so that's now going to be like that. So now we have another values for y, that's going to be 2, 4, and 6. So as you can see, the values are different, but the order of the values is the same. So if, for example, we would arrange these values in an ascending order, and we arrange these values in an ascending order, then the order will be the same. And vice versa, if we arrange this order, these values in a descending order, and then we do the same here, then again the order of the values will be the same. So this is monotonic transformation. But now let me introduce another transformation, which is minus 2x. So I multiply not by positive constants, I multiply by negative constants. Now for y we have the following order: minus 2, minus 4, and minus 6. So now if you want to arrange these values in an ascending order, you will start with minus 6, then it will be minus 4, and then it will be minus 2. So you see the order of values is not the same. So therefore, we do not have a monotonic transformation. So as I said, we are allowed to use only monotonic transformation if we want to have the same results of the optimization problem, and therefore, let's try to use this. So first of all, I'm going to remove these constants. So tell me please, is this a monotonic transformation or not? Yes, indeed. If you remove if you add negative, essentially to remove this constant means that we add negative constants, the same but negative constants. So adding or subtracting constants is definitely a monotonic transformation. Okay, now we are left with this term, and this term. Now what I'm going to do, I'm going to divide both terms by the first order utility, first order derivative of the utility, and here also. Tell me please, if I divide by the first order utility, first order derivative of the utility, will it be a monotonic transformation? Yes, this is a very good observation. We can multiply and divide by positive constants. In this case, in this case, that will be monotonic transformation, but we cannot do this with negative constants. So first order utility, first order derivative of the utility should be positive. Now tell me please, is it actually positive or negative for the utility function? Usually it is positive, right? So usually meaning what? Okay. Um, um, I, okay, if you find this person, tell me please. I will go to this person and I can make him happy just by taking money from him. Okay? All right. And don't do it yourself. Tell me. Anyway, so the derivative of the utility is positive for all kinds of investor, risk lovers, risk averse, risk neutral, and therefore we can safely divide by the first order utility. So when we divide, we get 1 here. So that's actually what we have. And now look here, when we divide second order utility by the first order utility, we actually get something which looks like, recall Kara. So this is Kara, but actually Kara is equal to minus, not just plus, but it's equal to minus second order derivative by first order derivative. And here we have plus. Therefore, let's introduce minus here so that we could just be mathematically correct. So here we have Kara. So this is our Kara, but let's not write Kara. Let's substitute Kara with eta. So this is our Greek letter eta. So this is coefficients of absolute risk aversion, eta. Okay. And now let's see. Let's now see how else can we simplify it, because this is not yet the end of the simplification. First of all, let's look at this term. Tell me please, if we remove this term, if actually we need to just add, it's negative, so let's just add this term. Will it be a monotonic transformation? So can we do this? Will it affect the results of the optimization problem? Yes, indeed, because the W0 is our initial amount of wealth the investor is going to invest, and therefore, well, obviously this is positive. Well, and this is constant, so it doesn't matter whether it's positive or negative, it's constant. So we just add a positive term, and then we just nullify this part, so we don't have it anymore. What else? Now let's look at here. We ideally would like to remove this rubbish as well. However, in this case, this is not possible to use it's not possible to use the monotonic transformation, because here we have this random term, W1. This is our end of period wealth. Right now, it's not known to us, so it's not possible just to remove it as it is. However, we still can remove it. Why so? Recall that we achieve this objective function using the second order Taylor series approximation. So we approximated this function about this value. So therefore, this number should be very small. And this number, when a small number is squared, then it's even smaller. So we can remove it kind of safely, meaning definitely we will lose a little bit of precision, but we can remove it just because this is going to be a second order term, which is just very small. I would say negligible. And that's why let's remove it. And therefore, let's see what we are left with. So we are left with a very simple combination. So as I promised, we have a linear combination of the expectation of the end of period wealth and a variance of the end of period wealth. So now this looks very simple. The only thing is that in addition to the expectation and variance, we also have eta, which is coefficients of absolute risk aversion. Now, so why we have it? Well, we have it mathematically because that's how we have it. So we just we obtained these coefficients because we wanted to get rid of the first order derivative. So we divided by the first order derivative here, and then we just get this coefficient. So it just appears here due to mathematical reasons. But this is actually very good that we have it. Why so? Because even though this linear combination is standardized for all investors, But if we don't have it, then it will be really weird. It would mean that the expected utility is the same. Well, this is not expected utility. This is a substitute for the expected utility. So it would mean that this kind of expected utility or a substitute for the expected utility is just the same for all investors. But we all know that investors have different risk preference. So we might have a standardized form, but this standardized form cannot be just, identical for all investors. There should be something in this formula which helps us to differentiate among different investors. And this is what helps us to differentiate among different investors. This CAR, which is different for different investors. Now, you might say the following, something like that. Okay, we get rid of this problem. So recall that our major problem is that it's really difficult to find out the mathematical formula for an individual utility function, because different people might have different utility functions. So it's very complicated and it's not done in practice. But then okay, we have removed this problem, we have solved this problem, but now we have another problem. We need to find Cara for our investor. So the thing is that actually finding Cara is much easier than finding individual utility function, because an individual utility function is actually a mathematical formula, while Cara is just a number. So do you feel this difference? One thing is to find a mathematical formula, and another thing is just to find a number, which is much easier. And this number can be found using some questionnaires, mathematical, well, some experiments, something like that. So anyway, this is something which is routinely done in asset management practice. This is just not a problem at all. There are some algorithm how it can be done, so it's just not a problem. Well, that's it for this slide, I guess. And now let's finally see how we can so recall that our original task is to find the weights uh, to uh, to allocate weights to risky assets and risk-free assets in such a way that we maximize the expected utility function, and in our case we actually maximize the substitutes of the expected utility function. Now we are on the way to find out directly how to calculate the weights under this condition that we want to maximize these substitutes of the utility function. So let us first consider a very simple case, and then we will move to the more difficult case, to a more difficult case. So this simple case is that we have just only one risky assets in the economy. So obviously we have risk-free assets, but also we don't have many risky assets as is usually. That's actually what we have in real life, but we have a single risky assets. However, it's not all that unrealistic as you might say. So you see, I have written here real markets, meaning that actually this might be quite a real situation for an individual investor. Why so? Because if an individual investor invests in so many risky assets, then his transactions costs will increase. However, what the investor can he can do he can actually find some funds, for example, mutual funds in Russian PIF, Payovoy Инвестиционный fund, so unit investment funds, which already contains many risky assets, and then this investor would invest into this fund, into these mutual funds. So these mutual funds will also be a kind of assets, risky assets, and investing into one mutual funds will be actually less costly. So the transactions costs will be smaller than when you invest into many risky assets. So in this case, if our investor has constraints on transaction costs, then in this he would prefer to invest into just one single risky assets, which is given by mutual funds. So as you can see, the situation is quite realistic. It's not just some theoretical abstraction. Okay, so let's see what we have in our market. We have initial wealth. Um, And then we have end of period wealth, which we don't know right now. Now, R is our a risky return, so return that you will get from risky assets. And by the way, recall, let me just introduce, not introduce, let me make a specification here. Recall that, well, I'm pretty much sure that you don't remember what I said in the previous lecture, but still, recall from the previous lecture that I denoted R to be a return on a risky assets without risk premium. And then I also added risk premium, relative risk premium. So relative risk premium is given by the star. So, and then I added to relative a relative risk premium and obtains a risky return or return on a risky assets. But now let's just make the notation simpler. So R, this R is now just, this one. So this is already a return, a final return on the risky assets, which already contains risk premium, which we usually observe in the stock markets. So, so once again, return with already with the risk premium. Okay, so this is the return on the risky assets. Now, Y is, as usual, this is our risk-free assets, return on the risk-free assets. And now we need to decide about proportions. So X is allocated to risky assets, and then 1 minus X will be allocated to a risk-free assets. So recall that what we are going to maximize, we are going to maximize expectation, a linear combination of expectation and variance. So expectation of the end of period 12 and variance of the end of period 12. Therefore, first of all, we need to calculate, we need to know how to calculate end of period 12. So let's look here. So this is our end of period 12. Our beginning of the period 12 with accrued interest. So this is interest that we will get from our risky assets. And this is interest or return which we will get from our risk-free assets. Essentially, we just have two gross returns weighted, and so this is essentially a weighted sum, weighted average return. Okay, you can open up the brackets, and if you open up the brackets and rearrange terms, then you will get another version how to calculate end of period wealth. And now, once again, our task is to maximize expectation and variance. So let's just express expectation of the end of period wealth and variance of the end of period wealth. So we'll take expectation of these parts of the right hand side, but you already see that everything here is constant. Everything is known to us at the beginning of the period. So we know how much money we will invest. We know what is the risk-free rates. We don't know the stochastic rates of the return, but actually this is the only variable which we don't know, because this is a random rate of return which will be realized at the end of the investment periods. So here we write expectation, but as for the rest of the terms, they will be all known to us before the investment process. So at the beginning of the periods, therefore, there is no need to write expectations anymore. So we only have expectation here. As for the variance, recall from econometrics that variance is calculated like that. And now if you actually substitute everything here into this formula, then you will come to this solution. Well, I think there are two intermediate lines between this line and this line. I don't produce these two lines here to save time and space, but these two lines, how to come from this line to this line. So these two lines are given in lecture notes. Now, we know how to calculate expectation. We know how to calculate variance. Now let's just take all this and substitute into our function, which we are going to maximize. And that will allow us to find how to calculate right weights. So now we can answer the question, what are right weights for our investor? Okay, so expectation of variance, I just, that's what we have here, the same we have here. And this is our linear combination of expected wealth and variance of wealth. So let's substitute expectation here and variance here. So after substitution, we achieve this objective function. So this objective function is going to be maximized. So maximized with respect to what? With respect to weights. We are going to choose weights in such a way, and also once again, we have just only two weights. One weight is going to assets, risky assets, and the other weight is going to risk-free assets. So we are going to find weight, and it's enough just to find only one weight because the second weights will be just calculated like that. So we're going to find weights given to risky assets in such a way as to maximize this expression. So as you can see, and so x is our choice variable. Choice means that we are going to choose weights in such a way as to maximize the objective function. And so we have this choice variable here and here. So we can say that our objective function is quadratic in the choice variable. What is good about quadratic optimization? A good thing about it is that the solution to the quadratic optimization is linear. Well, I think you all can take the first order derivative of the quadratic equation, and you all know that as a result you will come to a linear equation. So the solution will be linear, which is very convenient. Now, I guess again, I hope you all know how to solve optimizations problems. So you need to maintain the first order condition. So what it means, you take the derivative of this expression, derivative with respect to x, and when you take the derivative of this expression, you equate this first order derivative to 0, and then you use this formula in order to find x, in order to find weight. And this is the result, the solution. So, okay, this is the solution. And this is also the solution. The only thing is that you see that here we have first order derivative divided by the second order derivative, which is actually the inverse of Kara. So Kara is second order derivative divided by the first order derivative, but now we have just inverse. So that's why I put eta. Eta is the same as Kara, so I put eta in the denominator, and that's it. Then the two formulas are the same. So let's look at this condition, at the solution. So the weights, the optimal weights, the weights which will, well, optimal because we have solved the optimization problem. So the optimal weights means that we will get the right weights for our investor. So let's look how this optimal weight is dependent upon different parameters of our portfolio. So first of all, tell me please, what do we have in the numerator? So we have this expression, expected return minus risk-free rates. How do we call it? What do we have essentially in the numerator? Right, this is risk premium. By the way, this is expected risk premium, not just risk premium, but expected, because we are talking about we are forming a portfolio and we don't know what will be in the future with this portfolio, but we can actually have the expected return and expected risk premium. So we can say that weights, right weights, optimal weights is positively dependent upon the expected risk premium. So the larger the risk premium offered by a risky asset, the larger weights will be given to these assets. Does it make sense? Does it look logical, or does it sound logical? Right. Now let's look what we have in the denominator. In the denominator we have risk. Well, variance is risk or uncertainty. So now we can say, and we have inverse relationship. So the more uncertainty is the more uncertainty the asset has, the smaller the weights, the smaller weights is given to these assets. Again, does it make sense? Anyway, I think you all agree that it makes sense. And now also what we have here, eta, so kara. But here we have inverse kara. So how would you interpret this relationship? So we have inverse relationship with kara. Weight is optimal weight is inversely related to kara. So how could you interpret this? But can you just draw a connection between kara and weights? So what can we say? Like this inverse relationship means that. Just explain this relationship. Well, not real negative. It's inverse. It's not negative. It's inverse with a risk aversion. Okay. So the more risk averse the investor is, the smaller weights will be given to risky assets and the larger weights will be given to risk-free assets. And once again, it makes perfect sense. So as you can see, we have obtained a mathematical solution which also makes sense. So it's just, even from the economic points of view, it looks very logical and correct. Well, I guess that's it for today because we're now well, nearly running out of time. So I will continue the narration of the portfolio theory next time. I think we have, I'm not sure if we have tutorial or lectures next time, but anyway, I will check for it and then I will just, well, I will decide not decide. I mean, if I have just tutorial, I will assign you home assignments, but if I have lecture, then I will continue. Okay, that's it. Do you have any question concerning this material? Okay, looks like there are no questions. Okay. Okay, then that's it. Have a nice weekend and see you next time, next Friday. Goodbye.